Okay. Hello and welcome to another video on applied electricity. My name is Dr. Osman Hassan. I'll be solving the last questions, the last 30 questions under applied electricity first semester 2023-2024 academic year, right? So I'm going to continue from there. So the last time I stopped at question 90. Okay, so we are going to continue from question 90. But before I do so, as we are going to see, the last 30 questions, they are all based on chapter 1 to chapter 4, right? And I've done quite a lot of videos on these 4 chapters. So if you look at the quizzes that I solve, if you want to have a better understanding of the different methods and theorems, then go and watch those quizzes, right? So those videos are going to really help you to understand the concept, especially when it comes to some of the theorems. So they tend to be very hard for students to understand. But I believe if you watch those videos, it's going to go a long way to help you get the concept right, and then everything will fall into place, so you get the better understanding. Now, starting with question 91. Now, question 91. Let me enlarge this a bit. The following are statements about Kirchhoff's laws, except there are 2 laws of Kirchhoff, so this is true, right? Then Kirchhoff's current law is applied at a node, so that is true. And then Kirchhoff's voltage law is applied to an open circuit. Okay, so you can see that based on this, the only statement that is wrong is what? Okay, meaning the answer here is going to be C. I have C here as the answer. Now, let's go to question. That was question 81. Okay, now let's move to question 82. Millman's theorem is based on the application of A. Millman's theorem is based on the application of source transformation. So we have A, true, B, nearly true. It should be nearly true there. C, false, and then D, nearly false. So here the answer is going to be true. Millman's theorem is actually based on what? Application of source transformation. Why? Because if you look at Millman's theorem, it's actually, you have to get the equivalent circuit, right? Millman's equivalent circuit, which is what? Which is going to be an equivalent voltage, right? You have an equivalent voltage. Let's say equivalent voltage is in series with equivalent resistance. This is Millman's equivalent circuit. And then to find, for example, the equivalent voltage here, what do we do? It's going to be equal to the equivalent current times what? The equivalent resistance. And equivalent current here, we calculate it with what? Through the concept of what? Source transformation. So what we do is that you transform the voltage sources which are in series with what? With a resistor, you transform that to be current sources. Then you do the algebraic sum. So the answer here is going to be true, right? So it's A. Now moving to question 93. The operation of a Wheatstone bridge is better explained with the help of superposition theorem. Now here we are talking about Wheatstone bridge, right? Question 83. So we have a Wheatstone. When it comes to Wheatstone bridge, right, it's actually better explained by using Thevenin's theorem, right? Thevenin's theorem, because the place where you have the bridge, right, or you can call it the bridge resistor. So in order for you to explain how the Wheatstone bridge, right, what you tend to do that you remove that load, right, or you tend to make sure that you place there a galvanometer, right, and with the galvanometer you make sure that you adjust the resistors, right, one of the resistors, till you get a zero current, right? When you get a zero current, it means that there's no flow of current. So I mean that the current flow there is zero, and then that branch is what? Is open circuit. So question 83, this is what? False. Okay, so the answer here will be false. 94. The type of network topology depends on the kind of shape formed by the network resistors. So here is talking about network configuration, right, or network transformation. For example, when we have right, we have delta, right, or we can also have what? Y network. So you can see here the topology, right, it depends on the kind of shape formed by the network. So if the resistors, you arrange them in a what? Delta shape, we call delta network. If they are, you arrange the resistors in a Y shape, so we call it Y network. So here the answer here is what? True. So here is D. Okay, now moving to question 85. Resistance of a conductor is determined by resistance of a conductor is determined by I. So if I have want to calculate or find the resistance, how do you calculate or find the resistance? This is what it's all about. Now Ohm's law. Okay, yes, you can use Ohm's law to find the resistance by saying what? Voltage is equal to current times resistance. So you make resistance the subject, you get voltage over current. So that will give you the resistance. So this one is correct. Then an ohmmeter, right? So if you are at the lab and you are given an ohmmeter is a instrument used to measure resistance, right? Resistance. So that one is true. You can use an ohmmeter. Now a bridge, a Wheatstone bridge, right? A Wheatstone bridge too is also true. We use Wheatstone bridge to measure resistance, right? Like I was explaining earlier, you have an unknown resistor, right, which is any resistor. In that case, what you tend to do, you adjust a variable resistor till you get the current flow of zero. Once the current flow is zero, then you record the resistance. That becomes the resistance of the unknown resistor. So you can see that all of them are correct. So the answer here will be what? D, all of the above. Moving to question 85. The following materials have low resistivities except, okay, low resistivity. A, we have silver. We have B. So silver is having a low resistivity. I think I can't remember exactly, but it's 10 to the power minus 8 or something. So it's very small. The same for B, which is iron. Iron is also having a very small resistivity, which is also 10 to the power minus 8. Okay. Then we have mica, right? Mica is an insulator, actually. So that one is going to be what? The answer. We have DD, which is aluminum. Aluminum is also having a very low resistivity. Is the reason why silver, iron, and aluminum, they are what? Good conductors of what? Electricity, because they have low resistivity. So the answer here is what? C. A conductor has a diameter of 0.3 centimeters. So question 86, we have a conductor has a diameter, meaning D is equals to 0.03 centimeters, which is going to be 0.03 times 10 to the power minus 2 meters, and a length of 2.3 meters, right? So the length of this L is 2.3 meters. A length of 3.3 meters. Now the resistivity of the conductor is 10.3 times 10 to the power minus 8 ohm meter. So we have resistivity, which is 10.3 times 10 to the power minus 8 ohm meter here. Now you are asked to find the resistance, so determine its resistance. So question 87. Okay, 87. Now to find the resistance of this, you can see that if you are given a conductor, right? This is a conductor. Now with this conductor, the resistance, it depends on what the length of what this conductor, let's say L, and then the cross-sectional area, right? Let's say of this cross-sectional area, which is, let's say, A here, and so these are the two main parameters that we'll be looking at. So what is going to happen at the resistance, which is what? Going to be directly proportional to the length of what? The conductor. So meaning, let's say you have a wire. If the wire is very long, we expect to have a very high resistance as well. And then the resistance here is also inversely proportional to the cross-sectional area, right? So if the cross-sectional area is small, in that case, the resistance is going to be small. If the cross-sectional area is what? Large. So the resistance will reduce. So based on this, we can now get the formula for resistance, which is going to be, we bring equal sign, then you bring your resistivity over what? The area. So this is the formula, how you drive the formula. Once we have this, we just do replacement. So I have resistivity to be 10.3 times 10 to the power minus 8 times, times the length. Length is giving us 2.3 meters. And then we can see that when it comes to area here, we are given the diameter, right? The diameter. So let me get, from this diameter we can get the radius. So radius of this is going to be r, which is going to half of the diameter. So that will give me 0 point, right? So I get 0.03 centimeters divided by 2. That would be 0 point. So this will be 0.015 times 10 to the power minus 2 meters. Now that I've gotten the radius, so when it comes to now, I can get the cross-sectional area, right? The cross-sectional area, which is, you can see, is a wire, is a conductor. Here we assume that in that case the cross-sectional area is going to be a circle. So I have a area equals what? Pi r squared, right? Pi r squared. Now I'll come and replace the area here. I know my area is pi r squared, and r is 0.015 times 10 to the power minus 2 squared. So we get this. Now let me do the calculation of this. So I'm doing the calculation. So we are going to have 10.3 times 10 to the power minus 8 times 2.3, then divided by pi times 0.015 times 10 to the power minus, okay, yes, square. Okay, so we have to get this place is square. Till now encounter a problem here. Okay, I can use this, then divide it by it again. So we have this again divided by 0.015 times 10 to the power minus 2. Let's see. So you get 3 point. So yeah, so you get this answer. The resistance becomes 3.35. We can add 1 ohms. So the answer here is going to be D. Okay. Now moving to question 98. A household has 9 light bulbs of 60 watts each and are used on average 35 hours each. The unit cost of electricity is 6 Ghana per square. Calculate the total energy used. So this question 98 is about calculating the energy used in a household. Once we are talking about household, here the meter reading that we have at our various houses, right? They are reading there, or they are given in what? Kilowatt hour, meaning energy, right? So it's energy. The units there are in energy. So let's say question 98. They are in energy, right? And energy is in joules, right? And joule is just the same as watt hour, right? Sorry, watt seconds rather. Now instead of second here, we now use watt hour for this, and then we express the energy because they tend to be a very large value. We express in terms of what? Kilo, right? Kilo. So that's how we are going to. So now let's get the energy. So we have in the household, we have 9 bulbs, right? Of 60 watt each. So each of them is 60 watt. So meaning I can get the total power, right? Total power of the light bulb. The light bulbs is going to be equals to, meaning each one is 60, so that would just be 9 times what? 60. That will give us 9 times 60. Now it's going to be 540 watts. Okay, that's the power from the household with the 9 bulbs. Now to get the energy, so the energy here, we know power is the rate of work, and work done is a form of energy, so we get power to be equals to energy over time. But we're interested in energy, right? So energy is going to be equals to the power times what? Time. So meaning here with the total power that we've gotten times the time here, and that one should also be expressed in what we maintain the hours, because we are talking about electricity consumption in a household. So this become 540 times the average hours that we are giving. We have 35 hours on average, so we multiply this by 35, so we get the answer to be 18,900. Remember this we want watt hours, right? Because this in watt and this in hour. Now we change this to now to be in kilowatt hour, so that it's now going to be 18.9, right? Kilowatt hours. So the answer for this is going to be question A. Now moving to question 89. What is the total cost of electricity of the household in question? So here suppose we question 98. Okay, here's a mistake here. It has to be 98. In question 98. Now that we've gotten the energy, we can calculate the cost of electricity. That's if we know the unit cost, right? And the unit cost here, as we have been told, is 6 Ghana pesos. So 1 unit of electricity is going to cost 6 Ghana pesos. And the unit of electricity here, right? When you talk about unit electricity, we are talking about, we tend to assign 1 kilo, right? 1 kilowatt hour. A unit of electricity is just 1 kilowatt hour, right? So that means that 1 kilowatt hour of electricity consumed is going to cost 6 Ghana pesos. Okay, 6 Ghana pesos. Now I can calculate the cost of electricity consumed, because you can see the energy here that I have consumed, that is being consumed by the household, is 18.9. Again, now you can see that was also expressed in kilowatt hours. Then I can put here to be S. So this is about proportionality, right? Now based on this, the cost is going to be S, which is going to cross multiply. Now it's just going to be 18.9 times 6 Ghana pesos, which is going to be 113.4 Ghana pesos, and we change this into Ghana cedi. Okay, so in Ghana cedis it's going to be what? So you just divide by 100, so that'll be 1.134 Ghana cedis. So it's 1.134 Ghana cedis. So when we check here, the answer becomes what? B. Okay, we get the answer to be B. Now question 100. A current of 6 amps transfer a charge of 3,600 coulombs. The time taken to transfer the charge is, okay. So we have question 100. So we are interested in the time. So when it comes to what current, we know current is the flow of charges, right? Which means the formula becomes charge over time, right? So we make charge, we are interested in charge, so charge becomes current times time. So charge is now going to be equals to, from the question we are given the current to be equals to 6, then we are given the charge, rather we have to find the time taken, so meaning the time taken, so meaning here we make time the subject, so we have to find the time taken. So this becomes time here, which is going to be charge over what? Current. So time, which is going to be the charge, which is given 3,600 over the current, which is 6. So here it just be what? 600 seconds. So if you change 600 seconds to minutes, what do we get? Right? Meaning to get this to minute, you divide by what? 60 seconds, right? So to get this to minutes, so just 600 divided by 60. So you get the answer to be 10 minutes. So I'm going to get the answer here to be 10 minutes, which is D. That is for question 100. Okay. Now let's go to question 101. Preamble 1. Answer question 101 to 102. Okay, so the first two questions below this preamble. A circuit has a voltage source Vs of what? 24 volts. So meaning Vs is equals to 24 volts. And in series with its internal resistance Rs of 4 ohms. So mean Rs, the internal resistance Rs is giving us 4 ohms. If a variable load RL with resistance ranges from 0 to 50 ohms is connected to the voltage source and its internal resistance to form a closed circuit, right? So what that means that now we get this one. I have my voltage source, which is Vs, then I have Rs. Now you connect to this a load resistor, and this is a variable load, so meaning you can adjust the resistance within a range, and the range here is 0 to what? 50 ohms. Now that's the question. Now that's the preamble. Now let's move to the question. Question 101. What is the RL, mean the load resistor value that will dissipate the maximum power transfer. So this question is about maximum power transfer. And remember I said when it comes to maximum power, here is our load. This is just to say that if you want to get the maximum amount of power dissipated by your load resistor, you just make sure that your load resistor, it has the same resistance as what your internal resistance, which is Rs here. So you can see the internal resistance is given as 4 ohms. So that means the load resistance here will be equal to what? 4 ohms. So by selecting 4 ohms resistance as your load resistance, then you get the maximum power. So the answer here is going to be B. RL will equals to 4 ohms. Now 102. Calculate the maximum power dissipated by the load. Now that we've gotten this, you are asked to find the maximum power dissipated by load. Now that we've selected the load resistance to be equals to 4, meaning I can just, let me sketch a new one. So this is 24. This is 4. Ohms. Now to get the maximum power, we've selected the listen to also be 4. RL here to also be 4 ohms. So now you are just to calculate the power, right? We are now to calculate the power now using this circuit diagram. And to calculate the power, even here there are several ways you can go about it, right? So the power dissipated by the load, which is PL, is going to be equals to, we can use this formula, IL squared times what? Its resistance, which is RL, right? Or we can say the power dissipated by the load is what? VL squared over R. So any of this, and this will be the maximum power, okay? Maximum power. Because we selected the load resistance to be the same as the internal resistance. So any of this formula will work. Okay? So let's use the first one in this sense. So let's get the current, right? So the current that is going to be flowing here, which is, you can call this IL, is going to be, again, 4 ohms, and you can see 4 ohms and what? The 4 ohms is in series with another 4 ohms. So the equivalent resistance for that part is just going to be 8, right? 8 ohms. So current IL will be equals to the voltage source with Vs over the equivalent resistance. So this becomes 24 divided by 8, and that gives me what? 3, right? So it will be 3 divided by 8, yeah, 3 amps. So the current is now 3 amps. So I'm going to come and replace this in the formula. So the maximum power will now be 3 squared times it's the resistance of the load, which is 4. This is now going to be, meaning 9 times 4, which is 36. So we get 36 watts for this. So the answer for question 102 is going to be what? D. Now moving to 103. The internal resistance of a voltage source can be minimized, right? Minus the load resistance. Okay. So here we talk about the internal resistance of what? A voltage source. I think I explained this. If the internal resistance if I have a voltage source, okay, I have, for example, Vs, then I have another internal resistance, Rs, okay. We have this kind of circuit diagram, and then maybe we have a load resistor here as well. Now, if I want to minimize the internal resistance, I want to make sure that the voltage across the load resistor is the same as what my voltage supply. So meaning Vs, I want to make sure VL is equals to what? VL, right? So that means that my resistor is just using all the what? The voltage. The load resistor is using all the voltage. So there's small loss of what? The voltage due to the internal resistance. So you can see that because of that, you have to get the voltage across what? The load resistor here. Here I'll be using voltage division rule because Rs and RL here are in series. So VL is going to be equals to its own resistor, which is R, over the sum of resistors in series, Rs plus RL times what? The voltage, which is Vs. So you can see that if I want to get these objectives, right? In order to make sure that the voltage across the load resistor is the same as the voltage source, that means I've minimized the internal resistance of the voltage source. So you can see that this part here, right? I need that part to be 1, right? So here has to be equals to 1. So this place, for me to get this meaning, I have to get RL over Rs plus S to be equals to 1. And for me to get 1, remember I'm having a load resistor. The load resistor, think of this as being variable. That one you can change the resistance, but the internal resistance of the voltage source is always fixed. It comes with the battery, right? If you're having a battery and the manufacturer says the internal resistance is 0.5 ohms, it's 0.5, you cannot change it. But when you have your load resistor, that one you can select any load that you want. So with this, we can only select the load. So that means that if I want to make sure RL, if I want to get 1, that means I have to make sure that my load resistor is very large, right? Or you can say at infinity, right? So if you have infinity, so infinity here, RL is at infinity over Rs plus infinity. So this will now be infinity over infinity, so you get 1. So that means that if I want to minimize the internal resistance of a voltage source, you can minimize it by what? Selecting a very large load resistance. So meaning you can have here increasing the load, A, increasing the load resistance, B, decreasing the load resistance, C, removing the load resistance, and then D, balancing the load. So the answer here becomes A, right? You increase your load resistance so that it's very large. Now moving to 104. In Thevenin's theorem, Thevenin's voltage is there. So in Thevenin's theorem, Thevenin's voltage is the what? The open circuit voltage, right? So this one you have to know this. So it's going to be A, closed circuit, that is wrong. B, source voltage. C is the open circuit voltage. D, draw voltage. So it's what? C, the open circuit voltage. The internal resistance of a current source can be reduced by. Now when it comes to a current source, how do you reduce the internal resistance? It's similar. This question is similar to question 103, right? So it's the same thing. Now let's say you have a current source. Now we are having a current source Is, and this current source is in what? parallel with what? A resistor Rs. Okay. Now I have my load resistor, which is RL. Now again, the objective is the same, right? I want to make sure that the current which is going through the load resistor IL is the same as what? The internal, the same as the current source. So that means that there's no any voltage drops due to the internal resistance, so that you can minimize it. So I write here IS, the objective is to get IS equals to what? IL. Now to get this, now let's get the formula for IL in terms of IS and then the resistors that we have. So IL here is going to be equals to, again, this is a voltage supply. You can see we have a node here, and then RS and RL, they are what? In parallel. So we use current division rule to find the voltage, that is a current that is passing through the load resistance. Current that is passing through the load resistance, which is IL. So IL here is going to be equals to, since RS is in parallel with RL, so we take the other resistance, which is RS, right, over the sum of the resistors in parallel, meaning RS plus RL, then times the voltage source, which is what? The total voltage here. So with this, we get this formula. And again, the objective is to make sure that the current source is the same as the load current. So that means I have to make sure that this part here is what? The whole of this part is 1. So RS equals to RS plus RL, which is equals to 1. So again, I can only vary or change the load. The RS is fixed because it's the internal resistance. So you can see that here, if I want to get 1, right, I would rather make sure that my RL here is very small, right? It's very small, maybe almost approaching 0. You can see it's very small value. So if this is very small compared to the load resistance, you can see that I'll get what? RS over RS. So if it's very small, that means you get here to be 1. So here you choose a very small load resistance. So that here, the internal resistance of current source can be reduced by using a larger load resistance. No, a smaller load resistance. The same by using the same resistance as the load resistance. No, a stronger resistance. So the answer here becomes B. You choose a smaller resistance. That is almost small. It's smaller compared to the internal resistance of the voltage source. Now moving to question 106. In Norton's theorem, Norton's current is the what? The short circuit current. So this one becomes what? C. A is what? Closed circuit, which is wrong. B is open circuit. C is short circuit, and then D the total current. So it's a short circuit current. The answer here is C. Now we are now in question another preamble 2, which is, and you have to use preamble 2 to answer question 107 to 109. Okay, 107 to 109. So okay, so the figure we are given figure 9. I think this one is here, but it's for this one, which is above this. This is the figure. Then 107. Find the current that flows through 2 ohms resistor. So I think this one, there was a mistake with this question. You can see, if you look at the circuit diagram, we have 45 volts. It's in series with what? 4 ohms, and then we have our 4.7 kilo ohms. So that place 4.7 kilo ohms there, they're supposed to be 2 ohms, right? So here it's not semi-set, so this will be supposed to be 2 ohms. Okay, and it was changed during the exams, 2 ohms. Now that this is 2 ohms, then let's go ahead and solve for this. We are interested in trying to find the current which is passing through the 2 ohms resistor. I mean, in this very resistor, the current that is passing through this 2 ohms resistor, which is 2 ohms. Okay. Now, to find this current, you can see here you are not given a specific method to use. So you can use any method that you like, you prefer, right? So looking at this question, the other past question, I use we use what, that one we were being forced to use superposition theorem, right? So if you understood that superposition, you can use it for this, right? Then beside superposition theorem, you can use other methods. You can use nodal analysis here. You can even use mesh analysis, right? Or branch current method. Any of these methods will work, right? Will work. Or you can even use Millman method, right? It will work because of this. You can frame it this way. Now I'm going to use the last one. I use nodal analysis. I'm going to be using nodal analysis to solve for this circuit diagram because it's faster, and then because of time constraint that we have. So in using nodal analysis, so I'm going to assign nodes. So I have node A here, then I have my node B. Then I'm going to assign current to each branch. So here I have I1. This branch I'm going to have, let's say, I3. And this one, okay, I'm going to make the current direction here to be entering. Because of here we have minus positive, I want to make sure that, so let me change this. So let me change, I have here to be current direction to be moving up. Okay, let me come here. So this is my I3, and here is our I2. Okay, now with this, once we've assigned the current to each branch, I can now apply Kirchhoff voltage law to node A, and then that node A is going to be my reference node. Then node B, I'm going to ground node B, so it's going to be grounded so that the potential there becomes 0. Then I have here to be VA here at this node. So we are now going to apply Kirchhoff current law at node A. So you can see with this that I1 is entering node A, I3 is entering, and I2 is leaving. So the sum of what? Node entering is equal to the sum of node leaving. So I can write I1 plus I3 is equal to what? I2. That's the Kirchhoff current law equation for this. Once I've done this, now I'm going to now express the current here in terms of their voltages, right? And then the resistance. So let's look at the first branch, right? So here you look per branch. The first branch here, you can see the current originate from 45 volts, right? 45 volts there. All right, so we take, and then from there it ends up at what? Node A, meaning VA. So we take the potential difference or the voltage difference. So where the current originates is the high potential, where it arrives is a low potential. So you can see it originated from what? 40 volts. So I'll take 45 volts minus where it arrives, the voltage it arrives at the node VA, which is our reference node. Okay, then over what? The resistors that are in the sum of what the resistors in that branch, right? So you can see why, because in that branch is the same current that is going to pass into all the resistors in that particular branch. So if you look at what branch, the first branch, 4 ohms and then 2 ohms, is the same current I1 which is going to be going through them. So even this I2 that I wrote earlier, here it was just the same, but that would be actually what? I1. So the same current I1 flows through 4 ohms and then that of 2 ohms. So because it's the same current, we get the equivalent resistance by doing the sum. So that would be what? 2 plus 4. Now we come here plus. We go to the what? The I3. I3 here again, you can see that one too is originating from what? Based on the direction, is originated from 15 volts and it arrives at the node, the reference node again, which is node A, and then the voltage there is what? VA. So I'm going to take 15, which is the higher potential, minus VA. Then over again, we look here. Again, we now look in that branch, the third branch. You can see in that branch 2, we have what? 6 ohms and 3 ohms. You can see they are what? In series. Why? Because the same current I3 is passing through them. So we get the equivalent resistance there as well. So that will just be the sum. So we get 6 plus 4. Okay, it's 6 and 3 rather. 3. Then we now get the last one, which is I2. Now when you look at I2, the direction here, you can see that one is starting from what? VA, right? So VA becomes a higher potential. Then from there it arrives at what? VB, which is the lower here. Then over now the resistance in the middle, right? The resistor that is in the middle there is only 5 ohms, so over 5. So we get this equation, then we simplify, and then that will allow us to get VA. Once we've gotten VA, now we can go and get the current later. So let's go with this. So here I have 45 minus VA. Here it becomes 6, right? Then we have 15 minus VA. This is plus 3, that becomes 9, will be equals to, remember VB is what? Grounded, so the voltage there is 0. So I just have VA over 5. So now what is left is for us to simplify this. Okay, now to simplify this, you can see the LCM here. We can multiply both sides by, meaning 6 times 9 times 5. 6 times 9 times 5. That will be 270, right? So you multiply this by 270. Here too you multiply by 270. That will be our LCM. Here too by 270. I'm trying to conserve time, so that the first part, 270 divided by 6, will be what? 45. So here is 6, 9. Yeah, so that will be 45. So 45 by 45. 5 times 45. That is going to give me 2025. Then this one 2 by 45, which is going to be 45 VA. Now this part is also now 270 divided by 9. That will be 30. So 30 times 15 is going to be times 15, 450, then 30 VA. And here is just what? 270 divided by 5. And 54. So you get 54 VA. So if you group like terms, so this one will be, you send all this right across. So I can just even add them 54 plus what? 30 plus 45. So we get here 129 VA. Then this one I'm sending this here. So here I have 2025 plus 450. That gives me 2,475. So VA is going to be equal to this divided by 129, which is 19.18. We can say 186. Okay, then 189. Okay, 19.119 rather volts. So that will be the VA. Once I've gotten VA, I can now we're interested in I1. So I1, like we saw, was what? 45 minus VA over what? 6. So that is now going to be 45 minus 19.19 divided by 6. So I1 is going to be equals to S times minus 1 plus 45 divided by 6. That will be 4.3, right? So I get 4.302 amps. So the answer here is going to be what? A. So that is for this question. Moving to question 108. Determine the voltage across 5 ohms. So here the voltage across this 5 ohms is just going to be the same voltage as what VA that we calculated. Why? Because here, if the current is moving from VA to VB, right? So the potential difference is just VA minus what? VB, right? So let's say the voltage across 5 ohms is going to be VA minus VB, and VB is 0, so I get here to VA. So here will be 19.19. So the answer here becomes D, 19.186. Now moving to 109. Solve for the power dissipated by 3 ohms resistor, right? Power devolved by 3 ohms resistor. So we go back to our circuit diagram. Where is our 3 ohms resistor? You can see the 3 ohms resistor, the current that is passing through is what? I3, right? So to get that I3, we already know that I3 will be equals to, again, we come to this, was 15, right? When you take the potential difference, which is 15 minus VA, divided by the resistors that are in series with each other. So we have 9. So I3 will equals to 15 minus 19.19 divided by 9. So this is going to give me 15 minus 19.19 divided by 9. That will give me minus 0.466 amps. So this is what the current. We are interested in the voltage, the power dissipated. So power, which is going to be power dissipated by 3 ohms, is going to what? The current which is passing through the 3 ohms. And here is what? It's I3. So let me just make the I3 square times its resistance, which is 3 ohms. So we get this one to be minus 0.466. Remember, square times what? 3. So power here is going to be square of this times 3. So that becomes 0. We get here to be 0.65 watts. So when you look at the answers here, is going to be what? The answer here becomes B. Now moving to 110. Ohm's law states that current through a resistor is inversely proportional to the voltage supply in a closed circuit at constant temperature. You can see here it's actually wrong, right? Ohm's law is saying that the current is directly proportional to the voltage supply in a closed circuit at constant temperature. So here is saying inversely proportional. So this one becomes false. So the answer here is C. It's false. Now 111 here. Preamble 3. Use figure 10 to answer question 111 to 113. Right? Now this question, you are given figure 10 and the circuit diagram. You can see we have what? 68 volts, and then we have series and parallel connection circuit combination here. So let's look at question 111. Calculate the overall equivalent resistance in figure 10. So this figure, I'm not going to sketch this, okay? So for me not to sketch this, and then we calculate the equivalent resistance straightforward. So here the equivalent resistance overall one will be equals to, if you look at the circuit diagram, we can see that 10 ohms here, we start at the very far left, right? At the left. So you can see, sorry, at the right rather, this is our right. We start at the resistors at the right hand side of the voltage source. We can see that we have what? 10 ohms. It's in series with what? 4 ohms. So the equivalent resistance there is going to what? The product, right? Sorry, the sum. So I'm going to have here to be 10 plus 4. Okay. Now that equivalent resistance is going to be now in parallel with 8. So I put comma here. It's in parallel with what? 8 ohms. Okay. So that part I've now also gotten this. Once we've gotten this part here, which is this here, you can see that it's going to be in series with what? 6 ohms here, right? Series with 6 ohms. So we have here plus 6. And the last part here is what? Going to be corresponding to in parallel with what? With 2 ohms resistor. So the whole of this is now going to be in parallel with 2 ohms here. So once we've done this, we can just get the equivalent straightforward. So the first part, which is what? They are in series, so we just get the sum, which is 11. 10 plus 4, that will be 14. It's now in series. plus 6. Now we do the next operation. Now we have 14 is in parallel with what, 8, so that is just going to be the product, right, over the sum. 14 times 8 over 14 plus 8. Okay. Then plus, now you bring the whole of that. This, so 14 times 8 divided by 14 plus 8 will give us 5.09091. Okay, then you add plus 6 here. Now again, we know this will now be parallel with 2, so plus 6, and then we get here to be 11.091. Now it's in parallel with 2 ohms, so we take what, do the last operation, which is 11.091 times what, 2 over the sum, so this will be times 2 divided by 11.091 plus 2. So that will give me 1.694 ohms. So when you look at the possible answers that we have for this, we have 1.694, which is C here. Okay, so we have C here. Now moving to 112, find the total current or main current. So once we've gotten this, right, we know that this is our equivalent capacitance. So now that's our overall equivalent. So we just now have what, our 68 volts is now and see what our equivalent capacitance is, sorry, our equivalent resistance, which is 1.694. so we're interested in the current, which is the current that will be here, I. So I here is going to be equals to the voltage source, which is 68, divided by our equivalent resistance, which is 1.694. That will now give us inverse of this times 68. So that will give me 40.13. 131, you can see 131 amps. So the answer here becomes A. Okay, A. Now moving to 113. Determine the current that goes through the 10 ohms resistor. Yes, this is become the difficult part, right? This becomes the difficult part. Why? Because we have to go back. So it's better now I remove this one. Okay. Now we have to find the current passing through 10 ohms. This is our 10 ohms. We are interested in the current, this current here. Okay. Now to get this current, we've just gotten the main current or the total current, which is 40.142. So you can see that that's our main current. So when you come to now our main current, you can see it's entering main current, which is 40.142 here. It's entering this node, right? Then it's going to get divided. So here is going to be our one I. Let's say this, another current is going to be here. But bear in mind that this part here, right? the whole of this part, we have to use the equivalent resistance there, okay, not the 6 ohms here. So you have to be careful when you are doing this. We have to use the equivalent capacitance, right? The other part except the 2 ohms. So when you come here, we already did that, right? Before we did calculate the parallel connection of 2 ohms and then the other equivalent capacitance, our answer was 11.091. So that equivalent capacitance, which is 11.091, is the one that we take, right? And then we use current division, so it's in parallel with 2 ohms, right? That's what this is about. So I'm going to come here. The current which is going to pass in through 6 ohms here is going to be, or let me use this one, the equivalent capacitance here, which is 11.091, because that's the one which is going to be in parallel with 2 ohms. Is going to be equals to the other resistor, which is in parallel. It is in parallel with, which is 2 ohms. This resistor 2 ohms here. So we take 2 ohms over the sum of resistors in parallel. So 11.091 plus 2 times the total current, which is what we calculate to be 40.13. Okay, here we got 40.13, they got 40.12. So let me use a 40.142. Okay, so we get this answer. Now the current here becomes, meaning we get 2 divided by 11.091 plus 2 times 40.142. So that gives us 6.133 amps. So we get this current, but we are not done yet, right? So once I've gotten the current, that will be the current which is passing through this 6 ohms here. So the current is the same as the current, the 11.091. So I will come here. This is now my current. So this current here is now what? The 6.133 amps. So when you come here, you see that it's also going to get divided again. But this time, that will now be the current that is passing through the 10 ohms. So to get this one again, we come here. We now have 8 ohms what? It's in parallel with what? Here we'll get to the equivalent capacitance for this part, right? Because the same current is going to pass through this. And which was what? 14. We did the part here. Okay, this part here, which was 14. So now I'm going to use current division rule again to get this. So I'm going to get current that will pass through the 10 ohms is going to be, now we have 14 ohms. It's in parallel with what? 8 ohms, right? 14 ohms is in parallel with 8 ohms, just like we saw here. Where is it? This part here. So I have this. Since I'm interested in the current that is passing through the 10 ohms, so we take the other resistor, which is 8, over the sum of resistors in parallel. Remember, here is in parallel with what? 14, right? The sum of 10 and 4 here give us, so 14 plus 8 times the current which is entering the node, right? is what? So we calculate with 6.133. So this is going to be equals to now times 8 divided by 14 plus 8. So we get this to what? 2.23. So the answer here, 2.23 amps. So this gives us the answer to be what? C. Now determine the current. Okay, see different one. So this will be C. Okay. So now moving to question preamble 4, right? Figure 11. Figure 11 here. Use figure 11 to answer question 20 to 21. So here the numbering is wrong. So here is supposed to be here the first question that I've loaded. So that will be 114 and 115 here. So you have to use figure 4 to answer question 114 and 115. So to do this, here, if you look at this circuit diagram, you can see that it's a bit complicated, right? So you can use other method to solve for let's say current. But even with this, from the question, you can see there's a restriction here, because 114, you have to find the equivalent voltage, right? Equivalent voltage implies here we have to use Millman's theorem, right? Millman's theorem. And then 115, you have to calculate the current that flows through what? The load resistor. Load resistor here is RL. This one here, the 182, that's the load resistor. Now let's use the Millman's theorem. So Millman's theorem is theorem. Okay. Now in using Millman's theorem, you can apply this to a specific kind of circuit diagram, whereby you have for several branches, right? That is excluding the load, right? You don't include the load here. This load, you exclude it. Then after that, if you can see that there's a pattern whereby for each branch we have a voltage is in series with what? With a resistor, right? So when you have a connection of these kind of branches, then in that case you can use Millman's theorem. So if you look at this circuit diagram, you can see that the first branch, which is here, we have what? 20 volts is in series with what? 240 ohms. The second branch, we have 40 volts is in what? Series with what? 200 ohms. And the last one, 80 volts is in series what? 800 ohms, right? So you can see this follow the pattern that I just talked about. That is excluding the load, which is RL, the load resistor. Now with this, we are now to get the equivalent voltage. So to continue, since we are using Millman's theorem, we have to get Millman's equivalent circuit. What that means is that where there's this pattern, right? Where there's the pattern is the part that we are going to what? Convert, right? So where we are having each branch, where you have a voltage is in series with the resistor, all that 3 branches, we have to convert that to what we refer to as what? Millman's equivalent circuit, which is going to be now the whole of what? Now going to have just one voltage, which we refer to as the equivalent voltage, and then now it's going to be in series with what? One resistor, which is one equivalent, we call it equivalent resistance. And once you've done this, you connect now to your load, right? You maintain your load resistor. Then I have my RL, which is 182 ohms here. So this is the how you get the equivalent. This is what we refer to as, meaning excluding the, right? Excluding the load resistor, we refer to this part as what? Millman's equivalent circuit. Now that we've gotten this, so we are to get the parameters for our Millman's equivalent circuit. So we are to get the equivalent resistance. So let's have equivalent resistance. So the equivalent resistance for this, right? Again, we are focusing on only this part, just the non-load part, meaning we imagine that this load is not existing yet. So once you've done that, you can see that if we were to now do source transformation, right? Source transformation of this, you can see we have voltage sources in series with what? A resistor. So you can convert that to what? To a current source in parallel with what? A resistor. So if we were to compare to convert each branch, we have 3 of them, right? So you now have what? These resistors are now going to be in parallel with each other. So as a result here, the equivalent capacitance here that we are going equivalent resistance that we be calculating here is just going to be there, and they are all going to be in parallel, right? So you think of them in terms of source transformation. So I now have what? R1 over 1 over R2 plus 1 over R3, because they are all going to be in parallel. When we have done this, you just replace the resistors, replace the resistances that we are giving. So I have here 1 over the equivalent capacitance equal over the equivalent resistance equals to 1 over, we have here the first one 240 ohms, then the second one is 200 ohms, then plus the last one, which is 1 over 800 ohms. Now you just use your calculator to do this. So I have 240 inverse plus 200 inverse plus 800 inverse. So that will give me 0.01. Then you do the inverse of that. So again, -6. Equivalent capacitance for this is equivalent resistance is going to be -6 ohms. Okay, equivalent resistance is -6 ohms. Now we've gotten the equivalent resistance. Now let's get the equivalent voltage. The formula for equivalent voltage is going to be the equivalent current times the equivalent resistance. Now to get the equivalent current, again, we think in terms of what? Source transformation, right? So let's say you are converting, right, the voltage source in series with what? The resistors to current source in parallel with each of the resistors. That means the first part here, when you are doing source transformation, right? So in terms of current source, to get the current source for, let's say, the first part here, imagine we are doing source transformation. So this place is going to be what? IS1, right? Will be equals to the voltage, right, over what? Divided by the resistance, which is 240 ohms. And here we pay attention because it's algebraic sum. Okay, you have to pay attention to the polarities of what? The voltage source, right? Polarities of the voltage source. So based on this, so the first part here, first branch, I'm going to get 220 over what? 240, meaning the voltage over what? The resistance. Now going to the next branch, again, here you pay in terms of what? Direction. So here is a positive, this one. So here is also going to be plus, right? Because this one, the direction of the current will be what, going up. So we get here to be what, 40, meaning the voltage, which is 40 over its resistance, which is 200. Then again plus the voltage here, which is the last one, which is 80, divided by its resistance, which is 800, over the resistor, which is in series with the, which is in series with. So we get this. Now I can just do the calculation for this. Okay, even just cancel a bit to reduce this. So I know my equivalent current is going to be, here will now be what, 12, right? 1 over 12 here. Here is going to be what, 0.4, right? This and this here will be 0, so this will cancel. So we get 80. So that will be 10. So 1 over 10 here. Okay. So 1 divided, let me start with the 1 over 10, which is 0.1, right? So 0.1 plus 0.4 plus 1 over 12. So I get the current here to be equals to 0.583 amps. So that is the equivalent current. Because if you look at the 114 here, we are asked 150, we are asked to calculate the current that flows through the low resistance, and to get that we have to get the equivalent, Millman's equivalent. So here becomes equivalent, we just got in the current, so let's get now replace it to get the equivalent voltage. This is going to be one equivalent current, which is 0.583 now. Equivalent resistance here for this was 96. So this times 96 here. So we get this one to be 56 volts. So here is 56. So now that I've gotten this, you can see now is we have a simplified version of our this one. You can see there. And then we have 56 volts here. So you can see now we have 56, 96, and then 180. So now you can see clearly that this is just a simple circuit, right? Where we have two resistors in series and then you have a voltage source. So the current which is going to pass through the low resistor RL is going to be equals to, right? Equals to, meaning it's the equivalent resistance RS in series with what, the low resistor. So we take the equivalent for that, that will be RL plus what's RL here. Then over here the equivalent. So the equivalent voltage will be over the sum of the equivalent resistance plus the low resistance. So IL here is now going to be in the voltage, which is 56, right, over the equivalent resistance is 96 plus 182, which is a low resistance. So I get 56 divided by 96 plus 192. That will give us 0.19. I think here. Okay. even with that, I think there's a mistake here. Let me check this well again. When it comes to the voltage, equivalent voltage, what did I get? I got 56, right? But there's amount that says there's no 56 volts there. So let's check. Okay. I think there's a mistake somewhere. I think it's here. This part here that. Okay. Here we have what? Here will be 40 divided by 200. Okay. So take 40 divided by 200 is 0.2, not 0.4. So here you have to be careful. Here is 0.2 here. So meaning this answer will now change. So now if I take 12 inverse plus 0.2 plus 0.1, that is going to give me the current to be 0.384 amps. So that's one will now be multiplied by this one to give me here with 0.384. So this times what's 96. So that will be 36.82. Get 36.82 volts. So here this part now should be 36. So now we get here to be divided by this 2, I guess 96 plus 192. That is going to give us 0.127, which is going to 0.1277. So that 0.128 amps. So the answer here for this is what? D. Now question, another preamble, right? Preamble 5. Use figure 12 to answer question 116 to 119. Now with this question, you can see with this question we are given another figure, which is right. We are given figure 12. Now with this we have I1, okay, and when it is I1 here is supposed to be the 12 ohms. So meaning I1 here is supposed to be for the first one, which is 12 amps here. Oops, 12 amps. And here will be for what? This one will be 3 amps. So this is how the question. So here is 3. Amps. Now question 116. What is the voltage across the 15 ohms resistor? So we are interested in the voltage across this. So since this one, you can see the currents. We have 2 currents, right? They are in parallel with each other, and then we have these 3 resistors being in parallel as well. So here we can simplify this because the currents here are in parallel. You can just do the algebraic sum for that. So algebraic sum here is going to be equals to, or you can call this the equivalent current. For this is going to be, you can see now, you pay attention to the direction of the current. So the current that is moving up, right, we're going to make it positive, and the current that is moving down will be negative. So because of that, we are doing algebraic sum. So I'll get 12, which is moving up, so that will be positive. 3 is moving down, So that is minus 3. So I get here to be 9 amps. So now I can even sketch a new circuit diagram whereby I'll have the equivalent current, right? Meaning 9 amps here. Then I can have the resistors being connected in parallel to each other. So I have this circuit diagram here. So this is say by this time 9 here. So I have my 10 ohms, 15 ohms, and then last one 30 ohms as well. Now that I've gotten this, we are being asked to find the voltage across the 15 ohms resistor. So there are several ways of going about this. So the voltage here, let's say we have here to be the voltage at this node, right? You see at this node, let's say it's VA. Let's say this is node A and this is our node B. So at this node A, you see it's the same node, right? So node B here is also the same node. So I can label here to be VA. Okay, VA. Once I've done this, that's one way of doing. You can use this technique as a way to get this one here. So I have my VA. So the current, right? If we were to now do again algebraic sum of the current, let's say the current that is passing through the 10 ohms, we make all of them to be going out, right? To be leaving the node. So you can see that I can write 9 amps doing the algebraic sum is going to be what? The sum of current. Only 9 amps is entering the node here, and then the other currents are leaving. So let's say we label here as I1, I2, I3. So I can write now here equals to I1 plus I2 plus I3. Once I've gotten this, I've used what? Apply Kirchhoff current law. That's what I did at node A. So now I can come and what? I1, right? Again, we pick the bottom nodes to be the reference node. So we make we ground that part. So node B here, you ground it so that the voltage at that node VB is 0. So we now have a reference node which is VA. The reference voltage here is VA. So with this, you can see the direction of the current. I1 is moving from V point node A to node B. So where it starts from is the higher potential. So I can write I1 to be what? VA minus VB. And the resistor which is between the two nodes, we have 10 ohms. So the same is going to apply for what? V1. V2 rather, right? Sorry, I2, which is what? V1 minus VB. Then from the node, between the nodes, we have 15 ohms. Then the last one was what? VA minus V, and here we have 30 ohms. So with this, I have VB is 0 for all these cases. So I get here to be 0. So I just have VA over 10 plus what? VA over 15 plus VA over what? 30. Now you solve for VA in this case. So VA, you multiply what? So this is not the only way you can solve this. You can even use current division rule to find the lesson. I'm just doing this way. This just comes into my mind at the moment. So I'm now going to have the LCM here to be 15 times 10 times 30 which is 4,500. So 4,500 times 9, which is 405. 4,500. Here, remember here is what will just be 15 times 30. So that will be what 450 VA, and here will be what 300, right? 300 VA plus the other one, which is 150 VA. Now we've gotten this. We are now going to just have our 4,500. So the sum of this, right? Meaning I have 450 plus 300 plus 150. So that will be 900 VA. So VA is going to be equals to the inverse of this times 4,500. So that will be 45 volts. So you get the answer here to 45. So once I've gotten this, now we come back to what? Question 111. What is the voltage across the 15 ohms? So the current I know, which is what? I2, right? Based on this circuit diagram that I sketched here, which was equals to what? VA minus VB over what? 15, right? Ohms. So this is 0, and now this is 45. So we get I2 to be equals to 3 amps. Okay, here we are. Oops, the first question, the VA. No, we are asked to find the voltage rather across what? The 15 ohms, which is okay in a way, it's 45. But once we've even gotten the current, we can just do the same thing. The voltage across this will be what? The current through the 15 ohms, which is 3, times its resistance, which is 15, right? Okay, it's even more comprehensive to do it this way. So now I'll get my 3 times 15. Then we get again the voltage across the 15 ohms to be 45 volts. So here becomes 45B. Find the current through the 10 ohms resistor in figure 12. So the current was I1, right? This was our I1. So the current here again, like we saw, is VA minus what? VB all over the resistance between them, which is 10. So we get here to be 45. Here we 0, 45 over what? 10, which is 4.5 amps. So the answer for question 17 is what? A. Now moving to question 118. Determine the current through the 15 ohms, which I already did, right? And that one was what? 3 amps. So the answer for this is D. And then 119. Calculate the current through the 30 ohms resistor. That one, meaning which was I3. Again, we have VA minus VB, and the resistor between them is 30 ohms, so which is 45 over 30. So here is 0. 45 divided by 30, that will be 1.5 amps. So this one we get B. And the last question, 120. Thus, theorem says that the current through an element in the circuit is the algebraic sum. Okay, let me reduce this. Is the algebraic sum of the current through the element if each independent source is acting alone. So this one is to what whose theory correspond to the statement here, right? So here from the statement here we are talking about theorem that says that the current through an element in the circuit is the algebraic sum of what the current through the element if each independent source is acting alone. So this is what superposition theorem. So the answer here is what? C. Okay, so that's the end for the solutions for Applied Electricity first semester examination 2023-2024 academic year. So I wish you all the best in your exams which you'll be taking tomorrow. Bye bye, and comment if you have any issue or you need any clarity. Comment below the video that I'll be posting on YouTube. Okay, bye bye.